Generally, network forensic investigation is a slow and manual process that requires significant expert knowledge. In the Apex Global Logistics incident presented to us, we have 9 days worth of packet capture, which consists of 129 PCAP files totaling over 50 gigabytes, millions of zip logs, and hundreds of thousands of suricata alerts. Manually analyzing this much data could take several days. Hence, to address this problem, we built an agentic LLM-driven system which uses over 50 purpose-built analysis tools to process network data. It performs programmatic attack chain reconstruction, meaning it does not just summarize logs, but identifies how the attack progresses through the network. It can run locally on a Windows laptop with Olama, or be powered by other LLMs like Gemini or Grok. Regardless, it is able to produce structured output report in PDF, Markdown, and JSON with MITRE attack mappings. This slide shows the architecture of our agentic network forensic system. At the top, the user interface can either be the command line interface through main.py or the web dashboard using dashboard.py. After which lies the brain of the system, the LLM, which can be Gemini, Grok, or Olama. It runs a tool-use loop where it decides which analysis function to call next based on the current state of the investigation. Connected to the LLM agent are multiple specialized tool modules like the Suricata and Zig parsers, PCAP analysis tools using T-Shark, the threat detection module that identifies IOCs and reconstructs the attack chain. As each tool is executed, the results are stored in a raw evidence dictionary and acts as a single source of truth for the entire system. This ensures that all findings are based on actual past data. Once sufficient evidence has been collected, the system moves to the findings builder stage, where the raw data is analyzed to reconstruct the attack chain. Afterwards, guardrails and validation checks are applied to ensure correctness and prevent hallucination. If all required steps have been performed, the system then generates a PDF report, Markdown version, and JSON that contains all findings. To summarize the data flow process, it begins with the raw input data, which mainly consists of PCAP files, but the system can also detect zip logs and suricata alerts based on the file name. The agent then enters the tool-use loop, where the LLM is given a system prompt describing all available tools and iteratively decides which one to call. As each tool is executed, its results are stored in the raw evidence dictionary, and evidence is accumulated over time. Once sufficient evidence has been collected, the system synthesizes the findings by mapping the raw evidence into report sections, then reconstructs the attack chain together with its key stages, and guardrails like hallucination checks, confidence scoring, and read-only enforcement ensure that the report output generated is accurate. Our agent has access to a wide range of tools as shown, which we can group into categories. First, there's the packet capture tools that use T-Shark to extract information such as protocols used, DNS queries, HTTP requests, as well as summaries of top talkers and anomalies in the traffic. There's also flow analysis built on NFStream, which helps detect port scanning, beaconing, and data exfiltration. Next, we have a Zig parser that can efficiently process log files and extract insights such as DNS anomalies, HTTP metadata, and file transfers. We also have a Suricata parser that analyzes alert data to identify C2 activity and affected hosts. Lastly, our output tools consist of threat detection that performs IOC matching, detects suspicious ports, and maps out the attack to the MITRE attack framework, after which the final reports are generated. Our agent follows a structured decision-making process. Starting with high signal evidence like suricata alerts, it identifies compromised hosts and C2 activity. It then checks for what evidence it is missing, and then calls additional tools to help fill in the gaps in information. After that, it queries more detailed logs from Zeek, checking for DNS queries and HTTP and TLS connections to get a better picture of the network activity. Once sufficient evidence has been gathered, The agent maps the findings to the MITRE ATT&CK techniques and generates the final report. One key feature of our agent is that there is a required tools list that it has to complete before it's allowed to finish. This means that if it tries to finish early, it will be prompted to continue running until all required tools have been executed. This ensures that the final report is as comprehensive as it can be and does not miss out anything.
Now I'll be performing a live demo of our agentic network forensic system. To run the agentic system, we must activate our Python virtual environment and simply run the agentic system with Python main.py followed by the input directory and the LLM provider we intend to use. The system will automatically detect all the files in the folder and perform a thorough analysis. In this demo, we are using the Ollama provider with the Q1 3.1 14 billion parameter model. The agent will start reasoning, and once it is done, we are able to examine the logs and look at all the internal tools that is called. As you can see, the agent is calling multiple tools in parallel. The LLM decides which tools to call based on what it has learned so far. After each tool call, a checkpoint is saved automatically. This means if the process crashes mid-run, it can pick up exactly where it left off. It will also generate a full and complete report under the report folder. Now let me show you the generated report. The report is structured into 6 main sections: executive summary, scope and assumptions, detailed findings, meteor attack mapping, timeline of events, and conclusion and recommendations. The report covers DNS analysis, HTTP and TLS activity, IOC alerts from Suricata, the full attack chain reconstruction with patient zero identification, meteor technique mappings, and actionable remediation steps. Everything here is auto-generated from the raw tool output. The LLM decides what to investigate, but the report is built automatically from what the tools actually found. We also built an interactive dashboard. Running python dashboard.py launches a web UI at localhost 8080. The dashboard automatically loads the latest report. On the overview page, you can see all the key metrics at a glance: size of PCAPs analyzed, number of Suricata alerts, affected hosts, and RDP attackers. The patient zero box immediately highlights the IP with Cobalt Strike confirmed and lateral movement targets identified. Below that, the top 10 Suricata rules are ranked by hit count. We also use the dashboard to run agentic system by providing the file path, LLM provider, and model. Switching to the findings tab, we have over 100 findings color-coded by severity. Each row shows the source IP, destination IP, evidence, and a confidence score. The DNS tab displays individual DNS records, with IOC flags highlighting DGA domains and beaconing activity. The HTTP tab shows HTTP requests including suspicious user, agents, and malware downloads. The Meteor Attack tab maps all findings to their corresponding tactics and techniques. The Timeline tab traces the full attack progression chronologically. And finally, the Agent Log tab provides full transparency into every tool that the agent has called, with pass or fail status and a summary showing hallucination risk assessed. That concludes the live demo of our agentic system.
For our key challenges, there are really 4 main areas. Firstly, the technical challenge was scale. We were working with a large multi-day dataset with 129 rate-acted PCAPs file, plus very large Zig and Suricata logs. So the problem wasn't just detection, it was also how to process that much evidence in a structured way. On top of that, because this is an agentic system using an LLM, we also had to work around the context and orchestration limit. Secondly, there are detection challenges. Since a lot of the analysis is driven by the IDS alerts and logs correlation, false positives are definitely unavoidable. At the same time, some detections can be missed or just not emphasized strongly enough by the agent, which is why manual review is still important. This is also the general challenge of telling apart benign activity from genuinely malicious behavior, especially in a noisy enterprise environment. Thirdly, there were tools limitation. The biggest one was that the PCAPs were rate acted, so we didn't have full payload visibility. So this means that we could infer a lot from the metadata, timing, DNS, TLS, and alert logs, but we couldn't always directly inspect the actual contents of what was transferred. Some tools like Yara are also optional or environment dependent. And Zig or Suricata results depend heavily on log quality. Finally, there are definitely performance issues. With a very large PCAPs files and also especially very large Zig logs, runtime increases a lot. So there's a real trade-off between speed, completeness, and accuracy. So in short, I would say that the agent is pretty useful for first-pass investigation, but it still needs validation and tuning when working at this scale. So for key findings, the agent was able to reconstruct the main attack story in 4 parts. Firstly, for initial access, it identified the patient 0 as 10.128.239.57. It also found about 2.19 million inbound RDP connection to their hosts, together with the combat strike activity, which strongly support an RDP-based compromise, followed by post-exploitation. Secondly, for the discovery and lateral movement, the agent found reconnaissance behavior that was consistent with tools like NetX, SoftPerfect, Nmap, and SQL scanning. It also detected SMB executable transfer from 10.128.239.57 to .36 and .34, together with WinRM activity, which supports the lateral movement deeper into the network. Third, for exfiltration, the agents link outbound activity to 10.sh, involving hosts from 10.128.239.20 to .21 and .57. Because the PCAP array acted, we couldn't directly inspect the full payload content, but the metadata still strongly supports an exfiltration event. Finally, for impact and deployment, the agent found signs that ransomware were likely deployed through SMB after the domain controller access. It also identified tactical RMM and screen connect as persistent related tooling, with remote management activities seen across multiple hosts. So overall, the Part 2 agent's results were broadly consistent with the Part 1 investigation report. The main attack path matched, although the manual Part 1 investigation still gives final details on some lower level evidence. I would say that because they were still broadly consistent, it is quite close to what we want, and it proves that there were still exfiltration events. But overall, it's still an AI, so there are definitely still improvements that can be made to this. So just to make sure that our part 2 output is really reliable, we basically did a small comparison here that you can see against our part 1 report. The good thing is that the main story still lines up. We got the same patient 0 and the same RDP base entry point, the same general lateral movement through SMB, RPC, and VRM, the same TEM-SH exfiltration path, and the same overall deployment pattern. So for us, this was important because it showed that the agent wasn't just generating suspicious looking results. It was really able to produce the core attack narrative that we have already established manually in part 1. Of course, it wasn't exactly one-to-one, but part 1 still had better details on some of the smaller evidence, and because the PCAP array acted, some conclusions still need human checking. So I'll describe it as broadly consistent like what I said previously. But overall, you can see that this comparison actually gave us more confidence, and it kind of conclude that our agent is still useful as a first pass investigation tool.
Now let's talk about guardrails and safety controls to prevent the agent from producing unreliable or dangerous output. Read-only enforcements. The agent operates in a strict read-only mode. There's a function called enforce read-only in our guardrails validator that intercepts every tool call before execution. It blocks any attempt to execute shell commands, delete files, or make network writes. The agent can only inspect and report it and cannot modify anything on the system. Hallucination prevention. This is our most important guardrail. The core design principle is that the LLM decides what to look at, but the report is built from what the tools actually found, not from what the LLM claims. Every tool results is stored in a dictionary called raw evidence. When the report is generated, our build report findings functions reads directly from raw evidence, bypassing whatever the LLM may have said in its chat output. So even if the LLM hallucinates an IP address or makes a wrong claim, the report will only contain data that the tools actually returned. We have a check hallucination risk function that extracts all IP addresses mentioned in the LLM's output and cross-references them against IPs found in raw evidence. If the LLM mentions an IP that doesn't appear in any tool results, it gets flagged. Our last run returned hallucination risk low with 0 suspicious claims. Confidence scoring. Findings with a confidence score below the threshold of 0.6, which is set in the validator, are automatically downgraded from critical or high severity to medium. This prevents the LLM from making overconfident assertions. Input and path validation. The LLM sometimes generates malformed tool arguments. Our normalize args function catches these before the tool is called. It substitutes real dataset paths, renames wrong parameters, and validates all IP addresses using Python's IP address module. Invalid IPs are rejected outright. Execution safeguards. We have a max iteration cap of 30 to prevent infinite loops. Report generation is gated. The agent cannot produce a report until all required analysis tools have been called, so it can't skip steps. And after every tool call, a checkpoint is saved to disk, so if the agent crashes or run out of memory, we don't lose the evidence collected so far. Here are some of our agent's limitations. Redacted evidence. The PCAP files in the datasets have been redacted. All packet payloads are stripped to 0 bytes. This means that the agent cannot inspect HTTP post bodies to see what was actually exfiltrated, cannot check for 7-zip magic bytes in uploaded files, and cannot extract malware samples for QAR scanning. We can only see the IP addresses connected to the TEM-SH via TLS. Our conclusions about exfiltration are therefore based on DNS and TLS metadata rather than payload content. These details, our Part 1 investigations naturally catches finer grained details that the agent may overlook. For example, a human analyst will immediately recognize that 10.128.239.20 and 0.21 are internal DNS servers, and that their high alert counts are inflated by resolving queries on behalf of other infected hosts. But the agent treats them the same as any other compromised host. The agent detects indicators independently but doesn't always correlate them across tools. For example, temp.sh appears in both DNS and TLS logs, but only the DNS site is linked to the exfiltration finding. A manual review will connect both data sources for a more complete picture. The agent is stronger at reconstructing the main attack path like patient zero, lateral movement, exfiltration, rather than capturing every supporting detail that a human eye would pick up during manual log review, where human validation is still needed. Firstly, for ambiguous finding, the agent flagged 10.128.239.132 with 151 Siri cutter alerts, but it wasn't clear whether this was just a compromised host or just a machine with cat installed. A human needed to look at the alert breakdown and determine that the host had tactical RMM deployed on it by the attacker, while the CapCut traffic was just an employee using a video editing app, not exfiltration. Second, cross-checking with the Part 1 report improved confidence significantly. When the agent identified 10.128.239.57 as patient 0 with 2.1 million RDP connections and cobalt stripe beaconing, we validated this against our Part 1 findings and confirmed they match exactly. Without that cross-reference, a standalone agent report would carry less weight. Thirdly, redacted evidence limited fully deterministic conclusions. We know the attacker connected to temp.sh via TLS from host point 57, but because the PCAP payloads are stripped, we cannot confirm what data was actually uploaded or how large the exfiltration was. The agent reports the connection metadata, but a human must acknowledge that the conclusion data was exfiltrated is based on circumstantial evidence rather than inspected payload content. The takeaway is that the agent is highly effective as a first-pass investigation tool. It processes 14 million zig log lines and 161,000 Suricata alerts in under an hour and produces a report that matches our Part 1 manual findings. But final analyst validation remains necessary, particularly for distinguishing infrastructure roles like DNS servers, filtering environments, specific false positives, and making attribution claims.
For cost, our system is quite efficient because we use local alignment execution, which means there's no need for paid APIs during analysis. This keeps the direct model cost very low while still allowing us to run large-scale forensic analysis. In terms of time, the runtime depends heavily on the dataset size. For our runs, the latest analysis took around 58 minutes, while a smaller run previously completed in about 18 minutes. This shows that performance scales with input size, especially when processing large PCAP and log files. For trade-offs, using local models improves privacy and reduces costs, but it comes at the expense of longer runtime. Additionally, when we aim for more complete and thorough analysis, it naturally increases processing time. Overall, the system is cost efficient for local use, but there is a clear trade-off between speed and depth of analysis. In conclusion, our agent is able to perform autonomous analysis by processing large volumes of network data without manual step-by-step guidance. It integrates multiple tools like PCAP processing, Zig, and Zurikata into a single workflow, which improves efficiency compared to manual investigation. In terms of forensic quality, the key findings produced by the agent are largely consistent with our Part 1 investigation, which shows that the system is effective for first-pass incident reconstruction. From a safety perspective, the use of guardrails helps reduce hallucination and improves the reliability of the findings by adding validation and confidence checks. Finally, the main takeaway is that the agent significantly reduces manual effort and improves analysis speed. However, human validation is still important to ensure correctness and to make final decisions.